Let's solve example 4. We have a triangular lamina formed by the line y equals 4 minus 2x and the x and y axes. We wish to find the center of mass of this lamina. So we'll start by drawing what this line looks like. The line is y equals 4 minus 2x, so we have a y-intercept of 4 and a slope of negative 2. The line looks something like this. This is 4, and if we want to know where this crosses the x-axis, we could set this equation equal to 0. 4 minus 2x equals 0. We have negative 2x equals negative 4. So 2x equals 4, divide both sides by 2. We have x equals 2. That is the x value where the line crosses the x-axis. Now we can use the formulas for the centroid to find the center of mass of this lamina. So x bar is 1 over the area times the integral from a to b of x times f of x dx. Y bar is 1 over the area times the integral from a to b of f of x, 1/2 f of x squared dx. The area is simply the area of this triangle. This is a triangle with a base of 2 and a height of 4. So the area here is 1/2 the base times height. We could integrate if we wanted to, but it's just a triangle. So 1/2 times the base times the height, and the whole area of this triangle is 4. So that's what we will use for the denominators here. Let's find the x component for the centroid. We have 1 over 4 times the integral from 0 to 2 of x times f of x, 4 minus 2x dx. I encourage you at this point to pause the video, take this integral, work through it completely by hand. Make sure you're comfortable with this. You want to start by distributing the x through to both these terms, take antiderivatives, plug in the upper and lower limit, find the difference, and you'll get a number for this expression here. So pause the video, take a moment just for practice, and evaluate that integral. If you solve this integral and then multiply by 1/4, you will have an answer of 2/3. So 2/3 is the x component for the centroid, or the center of mass. For the y component, we have 1 over the area, 1 over 4. We're integrating again from 0 to 2, and we have 1/2 times f of x squared. So we take 4 minus 2x, quantity squared. Once again, this should be a straightforward integral. We would have to expand out the 4 minus 2x, so FOIL that out, but this should be relatively straightforward to do. Once again, I highly encourage you to pause the video, make sure that you can solve this integral by hand, and if you solve it, you will get a value of 4/3. So we found here that the center of mass, x bar, y bar, well, the x component is 2/3, and the y component is 4/3. So if we think of our picture here, 2/3 is approximately here, 4/3, that's a little bit bigger than 1, so that's approximately here. So the center of mass for this triangular-shaped lamina is approximately right there. That's the point, 2/3, 4/3. If we were to take this point, we could balance the entire triangle just on this single point. Take a look at example 5. We want to find the centroid of the region bounded by the x-axis and the function e to the x from x equals -1 to +1. So once again, we want to draw a picture of this and then use the formulas for the centroid to find the centroid. So we'll graph the function e to the x. It looks something like this. We're going from x equals -1 to x equals +1. And it's good before we solve the problem to think about, intuitively, where would we guess that the centroid is? So we have quite a bit of mass here on the right-hand side and not very much over here, and it seems to be weighted more mass lower down. So I would guess that the centroid might be somewhere around, perhaps here. We'll find the exact coordinates as we solve the problem. So let's start by finding the area. This will be the denominator for both the x and y components of the centroid. So the area is the integral from -1 to 1 of e to the x dx, and this is hopefully quite a simple integral. Antiderivative of e to the x is e to the x. Integrating from -1 to +1, we input a +1, that's e to the 1, and subtract e to the -1, which is 1 over e. E minus 1 over e is the area of this region. Now the x component of the centroid is 1 over a times the integral from -1 to 1 of x times e to the x dx. This integral can be solved using integration by parts. Let's go ahead and work through that just for some practice here. So using integration by parts, we want to identify the function u, and we look here and we think of our acronym LIATE. There's no log functions, there's no inverse trig, there is an algebraic function which is x, so we will choose u to be x, and dv by default is everything remaining e to the x dx. Find du by taking a derivative, du equals dx. V is the integral of dv, the integral of e to the x is just e to the x. So finding the antiderivative here for x bar, we have 1 over a times, now we have uv, x e to the x, minus the integral of v, which is e to the x, du, which is dx. We're integrating from -1 to 1, so I'll put a -1 and 1 here for the x times e to the x term. And we'll continue on. We have 1 over a times x e to the x. This is 1 e to the 1, so e minus -1 e to the -1. So this is plus 1 over e. This is the expression that we get from plugging in the 1 and the -1 into this portion of the antiderivative. And then the antiderivative of e to the x is simply e to the x. So we subtract out e to the first minus e to the -1, 1 over e. This is a rather messy expression, so we'll just get a numerical approximation for the value. So this value is approximately 0.313. That's the x component for the centroid. The y component, we'll write down that formula, y bar equals 1 over a times the integral of f of x squared, e to the x, quantity squared, dx. Integrating again from -1 to 1, and then we also have a 1/2 here for the formula for y bar. So this equals 1 over 2a, and we are integrating e to the x, the whole thing squared. When we have e to the x squared, we can multiply the exponents together. So this is e to the 2x, integrating from -1 to 1. And once again, just for practice, let's think about solving this by hand. The antiderivative of e to the 2x can be solved using u substitution, but this is one of those substitutions that we want to be able to solve without having to work through all the steps, using the guess and check method, if you will. So we have 1 over 2a. The antiderivative of e to the 2x is e to the 2x divided by 2 to compensate for the chain rule. If we think of taking the derivative of e to the 2x over 2, we take the derivative of e to the 2x, which is e to the 2x, times the derivative of the inside function, which is times 2. The 2's would cancel, and yes, indeed, we get e to the 2x as the derivative. So we evaluate this at the upper limit and at the lower limit. Multiply by 1 over 2a. A, once again, is this value of the area. And if we plug this into a calculator, we get a value of approximately 0.772. So the x component for the centroid is 0.313, the y component 0.772, approximately. So x bar, y bar is approximately equal to 0.313, 0.772. So that looks like it would be slightly higher than what my guess was here. Somewhere probably around here would be the center of mass for this two-dimensional area. Let's solve example 6. Before we get to the actual example, we have a slightly more generalized expression for the centroid of a two-dimensional region. Let's imagine having a 2D region that lies between the curves f of x and g of x, where g of x is smaller than f of x. The centroid can be found by taking the difference of the curves for the x component, and for the y component, we take the difference of the squares. So the scenario here is that we've got some function f of x, which is a larger function, and below this we have the function g of x, which is a smaller function, and We are finding the area from x equals a to x equals b. We want to find the centroid of the region between the two curves. And these two formulas tell us how to find the centroid. They're really a generalization of the formulas that we proved for x bar and y bar in the single function case, so we won't worry about verifying these, but we will go ahead and use them. So let's take a look at the example at hand. We want to find the centroid of the region bounded by the function f of x equals x squared minus x, and g of x equals x squared minus 1. Let's go ahead and take a look at these curves in Desmos. The function x cubed minus x is this red function here, and the function x squared minus 1 is this green one. We want to find the area bounded by these two curves, which is this purple area here, and the centroid is going to be somewhere in the middle of this. Now, we're going to go ahead and guess what we think the centroid might be. So here's a point that we can move around. I'm just going to place this in the approximate location where I would guess that the centroid is. So I'm thinking about finding the center of mass. I'm just roughly approximating this. I would guess that it's somewhere maybe around there, maybe a little bit lower, something like that. So that's my guess for approximately where the centroid is going to be. We'll solve this analytically and see exactly where it is. Now notice that the region is bounded by the two curves from x equals -1 to x equals +1. We could set these two curves equal to each other, and actually it would be a degree 3 polynomial, so that'd be rather difficult to factor, but we could set the two curves equal, solve for x. We would have x values of -1 and +1, and those would be the limits of integration for these centroid integrals. So now that we've seen a picture of what these two curves look like, let's go ahead and analytically use these formulas to find the centroid of this region. So the x component is x bar equals 1 over the area times the integral from a to b, x times f of x minus g of x dx. The area here can be found by taking the area between the two curves. So let's just draw a rough sketch of what this looks like. The function f of x is here, and the function g of x is here. So the area can be found by integrating f of x minus g of x, the larger function minus the smaller function. We integrate the difference from the two x values. This is the x value -1, this is +1. So the area is the integral from -1 to +1. So our f of x function is x cubed minus x. G of x is x squared minus 1. And we could work through this by hand pretty easily, but we'll use Mathematica to find the value of this. And plugging this into Mathematica, we get an area value of 4/3. So that's the area for this two-dimensional region. That's what we use for the denominator in the x and y components for the centroid. So for the x component, we have 1 over a, 1 over 4/3 is 3/4, times the integral from -1 to 1, x times, and then we have f of x, x cubed minus x, minus g of x, x squared minus 1. We could distribute the x. We could integrate rather easily here. I would encourage you to pause the video, try to work through this by hand. It's good practice. But if you do that, you will get -1/5 as the answer here. That is the x component for the centroid. Let's write down the y component for the centroid. The formula is 1 over a times the integral from a to b, 1/2 times f of x squared minus g of x squared, integrating with respect to x. 1 over a, that's 1 over 4/3, that is 3/4, integrating again from -1 to +1. And then f of x squared, that's x cubed minus x, quantity squared, minus g of x, quantity squared. Once again, if we wanted to, we could expand everything out here. We're integrating a polynomial, which should be a straightforward integral. But plugging this into Mathematica, we get the number -12 divided by 35. So the centroid for this region, x bar, y bar, is -1/5 for the x value. The y value is -12 divided by 35. As a decimal approximation, negative 1/5 is negative 0.2, negative 12 over 35 is approximately negative 0.34. This point is the centroid, or the center of mass, for this two-dimensional region. Let's go back to Desmos and see what that looks like in the Desmos graph. So here once again we have the plot of the graphs in Desmos. There's our guess for where we estimate that the centroid will be. We'll see how close my guess is. But the actual centroid is at negative 1/5, negative 12 over 35. That is right there. Oh, the guess was actually sort of close, not too far off, but that is the true value of the center of mass. We could balance the entire two-dimensional shape on that single point at negative 1/5, negative 12 over 35.